Hello there guys, welcome back to another video. Make sure that you control yourself, make sure that you fix yourself, and in order to fix yourself you need to do full power pen and full explanations and full working outs. Okay, so you want to understand what did you do wrong. Well, you know what you did wrong and how to fix it in this case. Any question that we need to explain, any working out must be done fully in order to count as your full purple pen. Alright, let's get started. Now what we have here is we have the acceleration. Now the acceleration can be calculated. Now this is very easy and straightforward. So this is calculated from the gradient. Okay, now you guys do maths. How do you work out gradient? Gradient is the change in the y over the change in the x. Now the change in the y we know, sorry, the change in x we know it is 1.4, because we want to know in the first 1.4 seconds. So this is 1.4. Okay, this is there. Okay, we got this one, so somewhere in between. So 1.4 is going to be somewhere here. Okay, now they did it so that it is pretty much in this side here. You can see 1, 2. So you can see 1, 2, 3, 4, 5. Okay, let's go that for 1.4 in this particular case. So 1.4 is going to be there, and then the change in y-axis is going to be, this is the change in the y-axis. Okay, it goes from 0 all the way to 4. The change is 4, and the y is 1.4 in this particular case. Okay, so let me zoom out so I can put the answers there. Okay, so 4, and the answer is going to give us, is going to be 2.9. I'll just do it to 1 decimal point in this case. Now next one is we have the distance. Now how do we find the distance from a velocity time graph? So this is given, so the distance is given from the area under the graph or under the line. Okay, now the first 6 seconds, we want to know what is the first 6 seconds. Now the first 6 seconds is the whole shape here. The whole shape is 6 seconds. So what I'll do is I will draw the shape here, so therefore if you didn't see anything, you know. So first of all we have the triangle, okay, and then we have the rectangle, and then we have a small thing here. So we've got 1, 2, 3. So therefore we need to work out the area of these 3. So therefore we'll work out the area of the first one. So the first one is going to be half times 1.4 times 4. So this is the first one. Okay, now again, how do I know? So here we've already done it, the first one. Okay, 1.4, and then what we got is we got from 1.4. Okay, we got from 1.4 all the way down to this one here. Okay, and then we've got the last triangle, which is from 5 to here and then here. Okay, so we've got number 3, which is half times 1 times 4. Okay, good, and then we've got number 2. Now number 2 is just a square, so we got the length, which is 4, sorry, the width, and then the width, which is what? It is, so from 5 to 1 point, so is it 5 here to here. Okay, so it's going to be 5 take away 1.4. Okay, and then we just need to plug this into the calculator. Let me just use my calculator to fix this up. Okay, so this is 2 point there. This is 14.14. Okay, this is 2, and the area is the distance, is we add them together. So we add them together. Okay, and this will give me 19.2 meters. So the answer is 19.2 meters. Again, if you got this wrong, this is the full working out. So now you know how to get this done. Now this is Hooke's law, pretty much. So this is Hooke's law. We need to remember the equation for Hooke's law. F is equal to KE. The equation looking for the force. So the extension is this multiplied by the extension is what? Okay, now it tells you that the extension is this one here, so this must be converted, so this is power minus 3, okay, which is there we go. So we need to convert this. Okay, now the answer says appropriate number of SF. Now this is something that you must have learned from maths. Okay, now how do we know which is an appropriate SF in this case? Now if you look at the numbers given to us, okay, so you see that we have 1, 2, so 2, 6, and then 0, and here we have 6 and then 2. So therefore the appropriate SF has to be 2 SF. So the answer in this case is going to be 1.6 in this case. So the answer is going to be 1.6. Okay, that is the appropriate SF in this particular case. Again, so this is something that you should have learned from mathematics. Okay, from a maths teacher. Right, so let's go for this one. Okay, so the question says here, describe how the student can find the change in the length. So how can the student find the change in the extension? Okay, how can the student find the extension? First of all, in our 3 marks, the first thing we need to do is the student need to measure what? Okay, they need to measure the original length. Okay, of the spring at the start. Okay, so they need to measure the original length of the string at the start. Okay, okay, and then what happens is they need to measure the new length when spring is pressed. Okay, because look, if we go back to the diagram, okay, so this is the spring at the start, and now we are compressing it. Okay, so therefore this is the new length. Okay, and then the last thing would be what? So extension. So in this case, it's going to be the original length minus new length. Okay, so this is how it's gonna work in this case. Okay, in this case. Now, students find it difficult to find an accurate blah blah. Now, 2 ways in which we can do that. Now, the first way is look at this. Now, first of all, you can see that look how far the ruler is. There's a gap there. Okay. Now, the gap can cause you to misjudge it. So if you're looking from the top, then you can view the reading as this. Now if you're reading from below, then you can view it as this here. Okay, so you need to be here, so even if you're here, you can misjudge it in this case. So what you want to do is you want to do the following. Okay, so what you want to do is you want to do the following. The first thing is you want to move the ruler closer to the spring. Okay, so this way you know exactly, so you know where exactly the level is going to be. Okay, and now the second thing is what's happening here is you're the one, so the student is the one compressing it. Okay, okay, now when the student's going to press it, so this thing can move. So for example, if the student's holding it and when the student is leaning forward to read it, okay, so the student's finger can slightly move and so on and so forth. So we don't want this to happen. So what we can do Alright, so let's see. So what we can do is we can use, okay, weight slash mass to compress the spring rather than using finger. Okay, so instead of using the finger, we can just use this one here instead. Okay, nice and easy. Alright. Okay, so now this is an easy questions. Okay, so the equation is given to you. You just need to use it. So you're looking for height. So you're looking for height here. So you just rearrange. So you have height equal to GPE over mass times gravity. Now GPE we know it's 11. So 11. The mass we know is 0.2. And gravity we know it's 10. Okay, so we just use this and get 2.6. Here we go, nice and easy. Alright, so this one's easy as well. Okay, work out the kinetic energy. Half times the mass. How much is the mass? The mass we know. The mass of the ball is given to us here. So 0.4 there. Velocity we know it's 12. Now remember, it's velocity squared. There's square there, so we need to square this. So therefore, the answer that we get is going to be what? Okay, so here is the answer. Alright, describe how the energy transfers happen when the ball hits the wall. Okay. Now, first of all, let's take a look what we got. Now, calculate the kinetic energy as the ball is moving at speed. So the ball is moving. Okay, so the ball is moving, and then we have the wall. Now, if the ball is moving, so what do we have? So therefore, it already tells you before it has kinetic energy. The question is giving you the answer straight away. The question telling you, look, I'm going to give you the mark, but you need to be awake to get the mark. Are you awake? If you're awake, then you will see that. So therefore, it's kinetic energy. Okay, so kinetic energy transfers to what? Transfers energy transfers to. Now it's hitting the wall, yeah? It's hitting the wall. What's going to happen? Okay. Okay. So it's transferred to thermal energy. Okay, so hit it, transfer thermal energy. So mainly it's thermal energy. Okay. Okay. And how is this transferred? So this is transferred by mechanically. Via mechanically. Let me see. Yeah, that's the best word. Via mechanically. Now, mechanically means it's using force to transfer the energy because the ball is kicking, the ball is hitting the wall. All that kinetic energy is, and then when the kinetic energy hit the wall, that's a force. The ball is exerting a force on the wall. So all that kinetic energy is transferred to thermal energy to the wall, and a bit of sound energy. So mainly is going to be thermal energy, kinetic energy transferred via mechanically in this case. Again, fix yourself. We have this one. Now this one is straightforward. The weight. What is weight? Weight is a force. So you need to work out the force. So rearrange this. So force is equal to work done over distance. Now the work done, we know the work done is energy. So work done is energy. Okay. Now, for those who revise, you know this already. Otherwise, you'd be crying. 1800. The distance we know, the distance there. Look, they're giving you the mark for free. They even give you the equation. They tell you who's a way to get the mark, who is a way to get the mark, and the answer is 1500. Okay, now same thing here. So here, calculate the total work done. The total work done in this case. So therefore, we need to rearrange the equation. So total done is equal to work done, gravity, divided by the efficiency, multiplied by 100%. Okay, now the only thing which we're swapping is we're swapping this with this one here, because we're looking for the total work done. So therefore, now the work done against gravity is what? So we know that the work done against gravity is 1800. The question tells you 1800. So if you're awake, then we're going to find out. But the efficiency is 64 multiplied by 100. Okay, therefore the answer is 2812.5. Again, if you got this wrong, you need to wake up. You need, this is, so you don't even need to remember the equation. You just rearranging and putting the numbers in, rearranging, putting the numbers in. Okay. All right. Now this is one. This is a question that many of you did indeed messed up. Now, some energy is wasted due to friction. So friction is taken. Friction is taken completely. Okay. So friction, energy is lost by friction. Done. Okay. Now suggest another reason why some energy is wasted. Reason why. Suggest another reason why is energy wasted in this. Why is energy wasted? Okay, they're not telling you what form is energy wasted. They're telling you why is energy wasted. Why energy is wasted. Again, why is energy wasted? Not what energy is wasted. Okay, so the question is not telling you, is not asking you what energy is wasted. So energy is wasted as sound, yeah. That is what energy, yeah. The question telling you why is energy wasted. Why is energy wasted? Why is some energy wasted? Yeah. The question tells you that some energy is wasted. Why? Because of friction. That's taken. That's gone. Okay. Now, why is other energy, some energy also wasted? Now let's take what we got. Okay. Now let's look at the diagram. Okay. So this was happening. Okay. Okay. Now friction is gone. So we got friction here, friction here, friction here, friction here. Okay, friction here, friction here, friction here. Okay, even in the hands, there's friction, friction. Okay, friction is gone. We can't do that. Why is energy wasted? Friction's gone. We need to find another reason why energy is wasted. Okay. Now, if you remember by now, you guys had your sports day already, and especially you, for those of you who took part in tug of war. Okay, and when you were pulling on this rope, okay, what did you notice with the rope? Yeah, so you were pulling, the other guy, the other classes were pulling as well. What did we notice? What did we notice? What happened to the spring? So another spring, the rope. Okay, yes, you get friction, isn't it? So some of your hands were actually hurting because of friction. But there's something else happening in the rope as well. Okay, now the rope, okay, stretches. Okay, because of what? Because of Hooke's law. Because what's happening is, so the rope has high, so the rope has high equal to high spring constant. It means very stiff. So when you are applying force on it, so both sides are applying force on it, yeah, what's going to happen? It has a high spring constant. So it means that's going to take a great amount of force to extend it. So the rope stretches under that much force, yeah. And when the force stretches, okay, some of your energy, okay, is actually gone into stretching the rope. Okay. That's why that's where some energy is wasted in this case. Okay, so this is one mark. Indeed, many people lost the mark in this particular case, so you don't need to worry about that. But now you know the answer in this case. Now this is the trolley experiment, 6 mark. The equation is given to you there. Let's see how we can get marks there. Okay, let's take a look what we can do here. Right. Now, first of all, we want to have the basic stuff out of the way. Right. Now, here's our diagram. So first of all, we have is we want the trolley to move from a distance, a particular distance. So let's say this distance here. Okay, all the way till the end. Let's say the end in this particular case. Okay, so this is going to be our distance. So call it D. Now, how are we going to get the distance? Of course, we're going to use a ruler to measure the distance in this case. Now, what we want to do is we want to see how long will it take to go from here to here. Again, so we're going to use the time in this case. Now, how we're going to get the time? We're going to use a stopwatch in this particular case. Okay. Now, why do we need to use these two? The reason why we need to use these two is because we can use these two to work out the speed, especially the velocity of the car. So we can work out the velocity of the car in this particular case. Now, if we know the velocity of the car, then of the trolley, then we can work out the acceleration. Right? This is what we are going to be doing. So the first thing first is we're going to list down what do we need to work out. So first of all, in order to assess Newton's second law, so how the acceleration of depends on the force. Okay, so plan the thing first. So first of all, I'm going to write down the plan. So the plan is going to be to work out the acceleration. So first of all, acceleration is equal to change in velocity over time taken. Now, to be more precise, it's going to be the final velocity take with the initial velocity over the time. Now, since the car is not moving at the start, then the initial velocity is going to be 0, so therefore it's just going to be, okay, so I'll just leave it there. Okay, so we don't want to confuse people. Now, how we're going to work out the other part now? So we're going to have, okay, so velocity is going to be the distance per time. Okay, so distance traveled. Okay, so distance traveled. Right, using a ruler. Okay, time taken using a stopwatch. Okay, so this is going to give us the velocity and therefore the acceleration. Now the question is, how can we change the acceleration? How can we make it go faster and slower in this case? So this comes down to what did this come down to? This will come down to the force. Okay, so we need to have a hanger. Okay, so we need to have a hanger in this particular case. So remember, when we did the practical, we have a little we have a string that attached from the trolley all the way down, then we had a pulley here all the way down, and then we have the hanger to hang the mass on in this particular case. So the weight pulls down and then therefore it goes. Right, now if you also remember that we started with weight, we started with some mass on the trolley, and then we took out one of the mass from the trolley and we added it to the hanger. So this way, what we are doing is we're keeping, so the mass of the whole system is pretty much is the same. So the mass of the trolley plus the hanger is the same. So all we're doing is we're taking the mass from the trolley and adding it to the hanger in this case. Therefore, we have more weight on this side to put it down. Okay. So what we're going to do is we are going to suspend weight from hanger to produce a force. Okay, this is where the force is going to come from. The force is going to come from the weight that we added to the hanger in this particular case. Okay, now what we're going to also do is we're going to keep the stuff the same. Okay, so we're going to keep the step the same, isn't it? Okay, now how can we get the step the same? Okay, so keep mass constant. Okay, so by moving weights from trolley to hanger. Therefore, this is pretty much we're changing weights on the hanger, and therefore this is changing the force. So this is okay. So changing the weight on the hanger. Okay, good. Now, what else do we need to do? What else do we need to do? Okay, so we talked about how we're going to get the distance travel. So v over t, distance over time, distance travel, and we're going to use a ruler to measure that. Okay. Okay. Right. Now, what we can do is we can make this a little bit better. Okay. Now, what we're going to do is there's something else we're going to do. All right. Now, this here is to help us. I'll show you. So you see the runway. What we're going to do is we're going to tilt it. So we have the table. So we've got the table. We're going to tilt the runway a little bit. Okay, so we're going to tilt the runway a little bit in this particular case. Alright, so we're going to tilt the runway in for a little bit. Let me see, what is this thing? Can I click on it? I can click on it. Okay, so we're gonna. Okay, so we're going to do that.